Good afternoon and welcome to our first Algorithms and Data Structures lecture. I've met many of you earlier today in the lab session, and now we actually start with the lecture and the content after we had the Python introduction earlier this morning. So this course is an introduction to algorithms and data structures. And today we have this lecture, a double lecture to speed up with the content, as I informed you before. And we'll start looking today into what an algorithm, what a data structure is, but we will also discuss the organization of this course, and we'll continue with the content. So this is the list of contents, and this will become more obvious in the coming weeks. We are starting today with the introduction, and then in the coming weeks and months, we look into different data structures, like graphs, which are very generic ones. We'll see lists, trees, maps, and hash tables. And in order to run algorithms on them, our algorithms need to be efficient, and for that, we'll use complexity analysis to assess this. We will also see recursion, which is very helpful to work on certain types of algorithm problems. We also see how we can sort data. For sorting, recursion is very helpful. And then towards the end of the term, we will have a couple of advanced topics as well as an outlook into quantum computing. But this golden thread will become more obvious as we progress in the coming weeks. Today, we are starting with the introduction, and we will also start looking into graphs today. So, all of you have done some coding so far, and you have learned programming in your first semester, because most of you are from the second semester of one of our programs here in the department, be it AI or cybersecurity, whatever, from both English language programs as well as German language programs. So we do the lecture together for everyone in English. So you need to know programming, but if you want to build larger systems, especially the ones that maybe solve problems very efficiently or deal with lots of data, we need to think more about how we can actually build such algorithms. We need to think about data structures that allow us to store data that we can operate on. And in order to solve more sophisticated problems and solve these problems also efficiently, we need quite a lot of mathematics, in particular linear algebra, calculus, statistics, probabilities, and so forth. So that's needed if you want to build more complex software. And in this course, we will see how algorithms and data structures work. We will also see how we can build them efficiently. Sometimes there are certain trade-offs we need to make. We'll see some standard data structures and algorithms, but you will also learn the tools to build your own algorithms and data structures and do that efficiently. Now, what is actually an algorithm? Today in the lab session, we talked briefly about the Goodrich book, and I'll mention the whole literature later today. Um, in the Goodrich book, there is a definition for an algorithm, which says an algorithm is a step-by-step procedure for performing some task in a finite number of time. So we want to perform some task, maybe add some numbers, delete some data, find some friends in a social network, whatever. And we want to finish this in a finite number of time, what the definition says. And it's a step-by-step procedure. So we need to describe step-by-step how the algorithm would work. There are lots of different algorithm definitions. For example, Wikipedia said in the past when I created this course for the first time, or when I started teaching this course 6 years ago, Wikipedia said something like that an algorithm is a finite sequence of well-defined computer implementable instructions, typically to solve a class of problems or to perform a computation. So its instructions, they need to be well defined. So there's a finite sequence. We actually must be able to implement this. So not just some abstract instruction, but something that can actually be implemented in a computer. And we want to solve a certain class of problems or perform a computation. What we see here is a finite sequence, while the first definition refers to a finite number of time. These are two different things because this refers to the instructions, that the description of instructions is finite, while here it says that the execution time is finite. Both definitions are okay, but I have some problems, for example, with the finite number of time, because some algorithms may just keep running forever and deliver better and better results the longer they run. And at some point, I may have to terminate or just keep running. So that's why I'm not too happy with the finite number of time, but I'm fine with the finite sequence of instructions. But there are other definitions. So when I thought how I could define what an algorithm is, I would say it's a finite, unambiguous, and effective step-by-step procedure for performing some task. So I want to do some task. The step-by-step procedure needs to be finite, so a finite number of steps in the description. Unambiguous, so we must clearly interpret what to do, and effective means that it's actually executable. This is something we can actually run in a computer and not some made-up instructions that are just magic. So, which of these definitions do you find maybe the most helpful for you? If it's the Goodrich one, send a 1 to the chat. If it's Wikipedia, send a 2 to the chat. Or if it's my definition, maybe send a 3 to the chat. And we see which kind of definition is maybe the one you find most helpful. I think it's pretty much even for 1 and 3, which are in the lead. There are less twos. Um, and there's, as I said, not that one definition that is correct. I found another one somewhere on the internet which says that an algorithm would need to satisfy 5 properties for input, output, definiteness, effectiveness, finiteness. So we would have inputs that the algorithm would use, but maybe some algorithm doesn't need any inputs, but just calculates something randomly. But we would specify the output. The steps in the algorithm must be clearly defined, and it must also be effective so that it's actually doable. But this definition also says that the algorithm must come to an end after a specific number of steps. Yet some algorithms may just keep running and running to deliver better and better results. So the finiteness here is something one could argue about. But you see, there are lots of definitions. However, I rather prefer one of these short definitions than this long one, because I think it's just way too long and it takes like one slide here. Now, there are lots of example algorithms. Like Quicksort is a very efficient algorithm for sorting data. Binary search is an efficient algorithm for searching in a sorted sequence. There's the Strawson algorithm, which is a fast matrix multiplication, so faster than a naive matrix multiplication. And if you know any other algorithms, maybe you can turn on your microphone and tell us those algorithms or send them here in the chat. And since we are recording this, if you turn on your mic, you will be recorded. But if you send your answer to the chat, I will just read out what you have written without without referring to you. So we see some students referring to bubble sort or merge sort. Yes, these are other sorting algorithms. Fast inverse square root, okay. We also have this one in the slide deck, BOGO sort, sort of a really nonsense sorting algorithm. TikTok algorithm, so I guess TikTok algorithm is probably the recommender algorithm, which videos you would see. Dijkstra's algorithm for routing. So I think all of those are great examples. Also the fast Fourier transformation, A star, and lots of others. Most of the ones you have mentioned, we'll actually discuss in this course, like merge sort, bubble sort, fast inverse square root is one of the selected topics. We'll briefly see Bogosort. Breadth first search is also something we'll see. We will see A star. We'll see Dijkstra's. So a lot of the algorithms you mentioned, we'll actually see them in this course. Now, there is obviously other things, other more algorithms, maybe more specialized ones, like there are algorithms that train a neural network. So some kind of optimization algorithm combined with a backpropagation or an anomaly detection. So there are also lots of algorithms for this kind of stuff. Now, when it comes to algorithms, there are a couple of classification schemes, and I want to establish this terminology early on before we start looking into the organization of the course in a few minutes. So, there are lots of different criteria that allow us to classify algorithms into certain classes. For example, some algorithms are deterministic or non-deterministic. Non-deterministic also means stochastic. So deterministic means for the same input, I always get the same output. So, for example, an addition of numbers would be deterministic, while maybe the training of a neural network would be non-deterministic, or stochastic, or some other numeric problems, they are non-deterministic. In this course, we will see largely deterministic algorithms, but we will see some non-deterministic ones as well. And then if you have some form of repetition in an algorithm, some algorithms are iterative while others are recursive. So iterative ones, they would use a loop, while recursive ones, they would use a self-reference. So a function or method would call itself to solve the problem. We'll see both types of algorithms quite a lot, recursive and iterative ones. Then there are exact algorithms as well as approximate ones. So exact ones would deliver the return or would return the right, absolutely exact solution, while approximate ones would return a near optimal solution, but maybe in much faster time. In this course, we'll probably see a lot of exact ones, but also some approximate ones. Then some algorithms are greedy, some are non-greedy. So a greedy one wants to solve as much as possible in a specific computational step, while a non-greedy one wouldn't aim for always getting as much as possible in one step. We'll see some greedy ones as well as some non-greedy ones in this course. And then algorithms can be serial, parallel, or distributed. So serial would mean we have our sequence of instructions and we would run this, while parallel would mean we have multiple threads or processes to run these computations in parallel, or you could even distribute the computation among multiple machines. Most algorithms we'll see in this course are serial. For parallel ones or distributed ones, you would need to look into other courses because this course is a foundation course. So really almost everything we see here is serial, but some of these algorithms could be parallelized probably quite easy as well. So these are some common classification schemes. If you know some other criteria that would allow us to classify algorithms, feel free to share this because this list here is obviously non-exhaustive. There may be more classification criteria. Now we have algorithms and they are great for computing something, but we also need data structures. And data structures allow us to store, access, and manipulate data. So the Goodrich book says a data structure is a systematic way of organizing and accessing data. And accessing and organizing would also mean here change, manipulate, delete. So Wikipedia says a data structure is a data organization, management, and storage format that enables efficient access and modification. Maybe we don't need efficient in the definition because we just want efficient data structures, but maybe there are also just some inefficient ones. So this term here is maybe not that necessary for the definition. And there are plenty of data structures, and you've been using them already when you learned programming. So you typically have used a list or arrays. There are trees, different types of trees, like a B tree. There are stacks, there are graphs, and many other data structures. If you got any more data structures, just share them now with us in the chat, and we'll see which other data structures you have come across so far. Linked lists and queues, yes. We'll see linked lists and queues in this course. We will see list trees, stacks, graphs. We'll briefly look into B trees. One student has seen hash maps. We'll also see them. And there are many other data structures. So if you know a few more or you have seen a few more, just share them here in the chat. If not, we'll just go ahead. A heap, yes, a heap is a data structure. All right. Arrays, yes. All of that sounds good. And these are all examples, data structures. Someone mentions dictionaries. Yes, dictionaries. Dictionaries are some type of map. One student asks about so-called neuronetical systems. Maybe, I don't know if you mean like a neural network or something like this. It's also, well, a neural network, you run algorithms on that structure. Yes, hash tables. So lots of good suggestions here in the chat. And there are plenty of algorithms you use all the time, probably advanced ones. Recognizing voice, making online payments, friend recommendations on Facebook, playing against a chess computer, optical character recognition, and lots of other stuff. So you use algorithms all the time when you use a computer or some kind of digital service. Now, this course is not easy. That's first of all the reality. And I think wherever you study algorithms and data structures is challenging but it's a very important foundation to your future in computer science. So there was this mock-up here on the internet. I think it's just fake, but I found it many years ago. So Kylie Jenner asked for a book recommendation that made someone cry. And then this guy here answers data structures had algorithms in Java made him cry. I don't want to scare you, but obviously that's a tough course. It's an important foundation for the future as a computer scientist, because almost every job you'll have in computer science, you need to think how to solve problems and how to solve them efficiently. And that's what we are doing in this course. But there'll be a lot of guidance, a lot of examples, a lot of practice. So don't be scared. And we'll be able to manage all of this together. Now, in recent years, something has changed. We have much better generative AI systems than before, and we can use them also to generate source code. For example, if you want the quicksort algorithm, you don't need to type it from scratch. You can just generate it with some Gen AI tool like ChatGPT, Claude, whatever. And these tools work particularly well on a lot of foundation algorithms and data structures. Why? Because they have been trained on so much data. There are so many examples of algorithms and data structures on the internet. Now you're wondering, why do you still need to take this course? And this course is important, and this course is not too much about coding. Rather, we will see how we can solve problems efficiently. And obviously, we need to code them eventually. And Gen AI is helpful, and you can use some Gen AI help if you wish, but you still need to understand what you're doing and how to fix bugs in it. And in the written exam, I'll say more about the exam later, it's handwritten, so you still need to know how this stuff works. But this course is not necessarily too much about coding, it's about concepts, and we will code them and run those algorithms and see how they work. We will break them, which is more fun than just doing this on a piece of paper during the term. And these Gen AI tools, they are helpful, but you still need to know what you're doing. And if you purely rely on vibe coding, you'll get lots of code that runs inefficiently, probably a lot of cybersecurity issues in your vibe coded code as well, and lots of other issues. And you still need to review what actually came out. But yes, you can use Gen AI tools for a lot of that. You could simplify the previous code also if you wish and get a different implementation of Quicksort. But you still need to understand what Quicksort does and maybe when to pick Quicksort, when to pick a different sorting algorithm that depends a lot on your problem. And that's something that the Gen AI will not necessarily help you too much with. And these Gen AI tools, they work terrifically on these foundation algorithms, but once you apply them to your corporate problems, very specific problems for which there's not much publicly available training data, then these tools work less great. They still work, but less, and you still need to know what you're doing. And overall, I'm very interested in Gen AI since I'm an AI professor. And you can use Gen AI, for example, also to generate tests for your code. That's cool. You can generate documentation for your code. You could also specify tests and then generate code out of these tests. So there are a lot of opportunities actually, and you can get explanations of your code and get improvements. So all of this is really cool, but you still need to know the foundations and how to solve problems, because what we see now is with Gen AI tools, we maybe have an additional abstraction layer. So you can use some higher level descriptions, but we've always been doing that in computer science because 50 years ago, 60 years ago, a lot of people wrote code in assembly, then in C, then C++, then Java, and now a lot of people use very abstract programming languages. So the AI is just another layer of abstraction, but you still need to know how to solve problems. And Gen AI is cool, and you can integrate this also in an IDE, like for example, Cursor is a modern IDE that offers AI assistance. And you can use AI in this course if you wish, but you still need to know what you're doing. And also with regards to the exam, you need to understand how to write code and how to solve problems. Later in this term, we will also have a guest lecture. A friend of mine, he works at Google and he uses a lot of AI agents to help him with coding. He has reported on LinkedIn that he's now 10 times as productive as before. He will give a guest lecture later in this term in this course, and he will give you sort of an outlook about AI assisted coding. But you will also hear from him probably that you still need to know the foundations and that this course is still a very important component of your first year. Now, in my courses, what I always like is something that is called the map of computer science. It's something you can find on the internet, and it's publicly available and provides a very big picture of computer science. And with a lot of foundations and a lot of applications, and what I like in my courses is I always highlight the areas that are relevant to the specific course. So I have highlighted some stuff here that is largely addressed by this course, and we will zoom in and see what's relevant. So the course is about algorithms. We'll see lots of different algorithms. We will also see a little bit of machine learning. We will see one example machine learning algorithm, but that's not the big focus of this course. Then obviously data structures are super important. We will see them. And we have to think about complexity because we want to run these operations as efficiently as possible. So we need to think about computational complexity. And at the end of the term, there'll be an outlook into quantum computing and how quantum computing has impact on computational complexity. And we will also see a little bit of information theory in this course, especially with some of these machine learning applications that we will see. And we will use Python for the coding largely. So this is the map of computer science that we have zoomed in and that covers most, probably addresses most of what we're doing here in this course. This course aims at providing you with an introduction to algorithms and data structures. We will balance theory and applications. Theory is important, but we will write real stuff that runs because I want you also to be able to apply the theory to real problems and that you have the necessary foundations to learn new methods in the future. And we will look at some current research problems, in particular around quantum computing, which will impact computer science in the coming years. What you need to do or what you need to know to succeed in this course, you need programming skills, obviously, and you need mathematics. This course covers quite a lot of mathematics from your first semester. We will also cover some mathematics from your second semester. Sometimes there's a primer if there's maybe some very specific concept that you have not seen before or that we may need to revise. But we need maths for algorithms and data structures. But if you feel there's anything missing or you need help, let me know because I'll be happy to help and provide some additional primers or revision. The course looks the following. So you know from our schedule that we have these lab sessions, and these lab sessions, we have 4 of them on Fridays. We have one at 8, one at 9:45, one at 11:30, and one at 1 p.m. You can pick any of the lab session that you want. You can also come to multiple if you want. In the lab sessions, there's no lecture, there's no recording, but you will work on this course worksheet. And I have talked about the course worksheet today in the lab session where we had the intro to Python, that there is a mandatory problem that you need to do to sit the exam. There's an exam bonus problem, plus lots of other coursework, and you're advised to do all of it to prepare the best for the exam. Once you feel okay with Python, you can start with the mandatory problem anytime. That's what I also said today in the morning, because you would just look into the respective section of the book, and I'll mention the book in a moment. And in the lab session, I'm happy to help. Whatever you're working on with this course worksheet, I'll be happy to help. After the intro today to Python, you can start working on the Python primer. After today's lecture, probably you can start with graphs. At the latest, you can start with this after next week's lecture. And so the workload is the following. You're expected to come to 1 lab session every Friday. If you're not around in Deggendorf, you can also join via Zoom because the lab session is hybrid. It's also online. And you can ask questions via Zoom. Yet a face-to-face discussion when we discuss your problems is probably helpful. So ideally be on campus. So this is 90 minutes and we will have 90 minutes, so another 1.5 hours of lectures per week. And this week we're having a double lecture because we just need to get started with the content. So you actually have more content that you can work on in the lab sessions. Because like in the first lecture today, we need to talk about the organization of the course. So we'll have a double lecture this week. And this course carries 5 ECTS, so 5 credit points. Now, what is a credit point? 1 ECTS has an expected workload of 30 hours during the term for a student. Now, if we have 5 ECTS, the expected workload that you are supposed to spend on this course is 150 hours from now until the exam. Some students obviously spend more time, some spend less time, but it's sort of the expected time. Now, if we have lab sessions for 1.5 hours and lectures for 1.5 hours, that's 3 hours per week. But we have 150 hours, that's 5 ECTS. Now, a term takes approximately 15 weeks. That means the workload for this course, the expected workload, is something around 10 hours. Some spend less, some spend more time. And just going to the lab and the lecture is probably not enough. So you need to spend more time on maybe for preparing for the class, doing revision, doing further exercises, working on the coursework, preparing for the exam, whatever. So, and you're really advised to work on all the coursework problems here in the sheet, even though there's just one mandatory one, as I explained today in the morning. But all of these coursework problems, they will give you a lot of practice and challenge you further. And all the stuff from here could also be relevant to the exam. So the written exam may refer to the coursework and the content of the coursework. It does not mean that you need to remember all the solutions in here, but maybe one of these coursework problems introduces a concept, and that concept could be quizzed in the exam. But you don't need to remember all the solutions for the exam. And sometimes I just copy paste some problems from the coursework sheet into the exam. And then I see very quickly who actually did their coursework and who did not. You're still able to solve it in the exam if you didn't do all the coursework sheet, but you will be able to solve it much faster, much better if you did the coursework sheet. And 5 credit points means there's plenty of time actually for this course. And most of the content that I discuss here is in the slide deck, and some more content will be provided through my iPad here in the session. And in the lab sessions, you can work on the coursework. If you have questions on the content, on the lecture, we can discuss it there. We can do a revision there. So I'm there always on Fridays. And obviously, you can ask your questions also in German or any other language aside from English that I speak. Now we'll quickly come to the topic of the exam. So at the end of the term, you need to sit a 90-minute written examination. And in order for you to be able to sit the exam, you need to do this mandatory problem and submit it via iLearn, as I explained in the lab session in the morning. If you didn't attend the Intro to Python, there's a recording. I've explained all of this. And everything discussed in the class is relevant for the exam. Also everything in the coursework. And sometimes there are some further readings in the slides where I advise you to read some book chapter that could be relevant to the exam too. And my exams, they work via the following scheme. I think I'll quickly show you this, then you'll see what an exam could be about. I'll just open it. So this is the exam from last year, and you find all the past exams in my Nextcloud directory. So my exams, they take 90 minutes, and there are 3 problems. And each problem carries 25 points, and it's your task to pick 2 out of 3 problems. So it's your choice which ones you pick. So you can get 50 points at the most. If for whatever reason you pick 3 problems, then the best 2 will count. But you should really focus on 2 problems. You should still study everything in the course and prepare everything because you don't know what the exam may be about. But I like the scheme. So I did my master's in England at Imperial College, and they had a scheme like 3 out of 4 problems. But I asked at that time when I was a student, what would happen if I did all 4 problems? And they said the worst 3 would count. Here, if you do all 3 problems, the best 2 would count. But my advice is always focus on 2 problems. And then a problem is up to 25 points. You can look into the past exams, what they look like. But my advice is attend the lectures, do the coursework, and then look into past exams. There are every year some students, they only try to study past exams. They don't follow the lecture, they don't do their coursework. And this often leads to big trauma if there is some new content or some new types of problems. So follow the lecture, do the coursework, and then use past exams for further practice. But don't skip the content, don't skip the coursework. And by the way, then these 50 points would be the best mark possible, a 1.0. 49 points would be a 1.1, but a 1.1 is not a valid mark because we only got valid marks 1.0, 1.3, 1.7. So we always round this to your advantage. So if you have 48 points, you would get a 1.2, which is a 1.0 rounded to your advantage, while 47 points would be a 1.3. And you need 20 out of 50 points to pass. Then there's the mandatory problem that I mentioned that you need to do first to be able to sit the exam. And there is also in the coursework an exam bonus problem. If you do the exam bonus problem, you will get a 10% bonus. Concretely, this will mean 5 points on top of the score you got here. So say you get 40 points plus the bonus, it's 45 points. That would be a 1.5. Rounded to your advantage is a 1.3. Rather than 40 points, which would have been a 2.0. So the bonus can be quite helpful. And we discussed briefly, or the bonus problem is something you can't work on yet. This is problem 12.6 in this coursework sheet. It's a tree algorithm. It's only something we can do in a couple of weeks. So start with the Python primer, maybe the mandatory problem as you feel comfortable with Python, but don't look into the exam bonus problem yet because it's not relevant yet. And we have these past exams. So there's plenty of guidance and preparation possible. There is one more note. In a few weeks' time, you need to register for this exam. And every year, we unfortunately have this, or we had this situation that students sit the exam or they try to sit the exam, but they did not register. And that's a big problem because it creates a lot of work for our admin assistants as well as me. So it's very important you register for this exam in Primus. In a few weeks' time, there will be a round mail from the Center for Studies for exam registration. And for this course, there are 2 exams you need to register. It's one, the written examination, as well as this mandatory problem. Often this is called in our Primus system either Leistungsnachweis or Übungsleistung. You need to register for both examinations. Otherwise, we're unable to process your case. And if there are any problems with Primus, you don't know how to register, please don't get in touch with me. I don't have access to Primus. I don't know what the examinations are called. If there are any problems with registering in Primus, ask the Center for Studies because they know they have access. I don't have access to the portal. So I'm unable to help. And we have the admin assistants for that, and they will be more than happy to assist you with that. Are you all okay with the organization so far? Maybe just some thumbs up or thumbs down, whether this is all clear or if there are any questions about the organization of the course. If there are questions, send them anytime in the chat or turn on your mic. So looks all clear. Then most of the content of this course is based on 3 books, plus obviously some other references. I like a lot this Data Structures and Algorithms book, which was published by Michael Goodrich and 2 co-authors. This book is from 2013. It's a very helpful book. It's maybe not up to date with regards to the latest Python version, but this is not a Python course, but we use data structures and algorithms. and we code them in Python because Python is a very simple programming language, as I explained earlier today in the lab session. So this book is great, and I'm not aware of any new version. That's why we just keep using the 2013 book. For specific algorithms, the Sedgwick book is quite helpful. Algorithms, as far as I'm aware, the fourth edition is the latest one. And we will look also into computational complexity. For this, I recommend the Sipser book, Introduction to the Theory of Computation. This book covers complexity, but it covers also a lot of theoretical computer science, which we don't do in this course. But if you want to learn more about theoretical computer science, this book is really cool because it also explains a lot of proofs in detail. So in case you want to study such stuff more, in addition to this course, I highly recommend the Sipser book. The key book to this course is Data Structures and Algorithms, and you can either buy the book or you can also access it for free through our library. I mentioned this earlier today in the lab session, and that you can use the library network to read that book, or you just buy it or whatever. So, but you don't need to buy it, as you can access it for free through our library. Now, you will notice that this course has been recorded before. It's on YouTube from last year. This year, there are quite some changes. Um, for example, I've extended the Dijkstra's algorithm. I've extended complexity analysis a little bit. I've talked more about AI-based software development, and there will be even a guest lecture. I've extended hash tables and quantum computing and sorting. There's a sorting algorithm called bucket sort or radix sort. I've extended this one, but these are just minor extensions, I would say, and there are obviously many minor improvements. I've also added in this selected topics chapter a subsection that is called a selection. And as there are sorting algorithms, there are selection algorithms to pick a specific element from an unsorted set or unsorted list. And these selection algorithms are new this year, and there is a specific one that is particularly interesting. It's the median of medians that I have added. And we'll be discussing that one this year. So it's important you follow the lecture, because if there are new topics and they are part of the exam, you're in trouble if you don't follow the lecture and you just look into last year's exams. We've done the intro to Python in the lab, so we're not doing them now. And we have, like this, finished the introductory chapter. And I've mentioned this median of medians and selection algorithms. This is in a topic or in a chapter that is called selected topics. And selected topic means there are lots of different algorithms. We will not be discussing all of them, but every year I just pick some of them, and the ones that I pick are relevant to the exam. Obviously, the other ones that we don't discuss, they are not important to this year's exam. String matching is anyway in the coursework, and it's explained well in the book. And when I started teaching this course, I only started with one or two selected topics, and now every year I keep adding something. So this year I added selection and median of medians because I just wanted to stay busy during the Christmas holidays. So usually every year during the Christmas holidays, I spend a few days on updating this course and adding some new algorithms. And so this year we will cover some selection of these algorithms. We'll see how the term is progressing. This is so far the introduction, and I've briefly talked about the selected topics. And with that, we can start directly with graphs. So graphs are a very, very generic data structure. And the good thing about graphs is they're highly generic. And once we have looked into graphs, All the other data structures we will see, like lists, trees, maps, and hash tables, they're just a variation of graphs with some constraints. And we will eventually just build more constrained algorithms on these graphs, while in the beginning in this course, we look into very generic graph definitions, very generic algorithms that run on these graphs, and everything we'll do next will be just more constrained. So we are starting from a very generic perspective and then get more specialized. One could teach this course the other way around, obviously, starting with simple constraints and then getting at the end of the course to the more generic part. But I prefer to start with the generic data structure, and then we actually have all the tools we need. Will be a tough start, but after that, you'll be able to build simpler data structures and simpler algorithms relatively easy. So it's a steep learning curve. And we will look today into graph definitions. We will see applications of graphs in computer science, so why graphs are so important. And then we see two very generic algorithms on graphs, which are shortest path and lowest cost, plus the A-star algorithm. So the shortest path and the lowest cost, it's something like the Dijkstra algorithm, but from a different perspective. Because some of you mentioned Dijkstra when I asked you for which algorithms you actually know. One person also mentioned A-star. We will also briefly look into that one. Now, we will switch to my iPad. So just wait for a second until I'm screen sharing my iPad. So we will look into graphs. And for graphs, so graphs are our chapter. But before we start looking into graphs, we need something that is called the Cartesian product. So we have two sets, A and B, and the Cartesian product is denoted as A, and then we have this X or cross B. And what this will return us is a set of tuples, and we have tuples in there, which are A and B. And small a and b come from the sets A and B, respectively. So A is, the small a comes from the set A, and B comes from set B. Who of you has seen the Cartesian product and this definition before? So if you have, maybe some thumbs up, and if you have not seen this, thumbs down. But probably you have seen this in your first semester. So everyone seems to be fine. However, we'll do a very quick revision of the Cartesian, and there's at least one person who didn't see it, and that's fine. And that's why, because we have exchange students, we have some high school students who signed up for this course. And that's why we'll do a quick example. So we can say A is 1, 2, and 3. So A is a set, and in a set, we have elements, but they are unordered. And we start a set with these curly braces, and they are unsorted, and we are not allowed to have duplicate ones in. So we have set A, which is 1, 2, 3, and we have set B, which are X and Y. And now what I want is the Cartesian product of A and B. And what we got in there are tuples. So this one is a tuple. A tuple starts with a parenthesis. And in a tuple, we have elements, but they are sorted. So a tuple is something different than a set. And in a tuple, we could have duplicates if we wanted. And so the elements within the tuple are sorted, but all these tuples are in a set. So the tuples, within tuples, there's order, but the order in which the tuples appear is not defined. So, and we say that small a comes from the set A and small b comes from the set B. Now, let's see which elements would be in here. So, we can, for example, start with 1 and x. That could be the first element. So 1, x. Then we can do, for example, 2y. And I want you now to continue this. We need 4 more tuples. So this set will have in total 6 tuples. And I want you to tell me the remaining ones. And once you have them, send them to the chat. So I'll give you a moment. We got already a few answers. So one is 1y, because we have 1x and 1y. And we have 2y, we have 2x and 3x and 3y. Remember, because this is a set, the order of the tuples does not matter. So you could have a different order of these tuples, but the order within the tuple is set. So you're not allowed to have element y3. It must be 3y because you first have A and then B for this Cartesian product. And the answers you sent here in the chat look fine. While I didn't review all of them, we've put them here now. Now, this was just the prerequisite because we need the Cartesian product. And we will now define graphs. And a graph is a tuple of 2 sets V and E. And V is a set. V is the set of vertices and we can also denote a sample graph. So we actually see what all of this is about in a moment. So imagine we have an example here. And I'll just take the one from the slides. So we have different vertices. Sometimes these vertices are also called nodes. And these vertices, they have a name or a label, which is here just an integer. So if this is my graph, what would V look like? If you have suggestions for what V would look like, maybe send this to the chat. We'll look into the connections between the vertices later. So V is a set. That's why curly brace, which is 1, 2, 3, 4, 5, 6. Obviously, it would also be correct if you write 1, 3, 2, whatever, because there's no order in this set. So this is the first part of the graph, but then we can put in connections among these nodes or vertices, and these connections are often called edges. We can put in some edges, and we can wonder what these edges would look like. So we said our graph is a tuple of a set of vertices and a set of edges. We've defined V for the example. Now we can define E for this example here, and we can say it's a set of, well, I don't know where this came from, but it disappeared. It's a set of tuples, because the tuples are the connections. But tuples will only come later when we actually have directed graphs. So this is actually an undirected graph. So what we see here, for example, this connection here, later we will see that they go in a specific direction and we use tuples. But here it's a direction both from 1 to 5 as well as 5 to 1. What we see is, there's no specific direction. We could add directions, but we will do this later, but not for now. So if there is no direction between 1 and 5, we don't use a tuple, but we use a set as well. So we can say there's a set of 1 and 5, because 1 and 5 are connected, but there's no direction. Then we know that 1 and 2 are connected, 5 and 2 are connected. We could also obviously write 2 and 5 because there's no connectivity or there's no direction. So this one would refer to this. And what I want from you is you can tell me the remaining edges and send them to the chat, which other ones we have, because we have done 3 of them now and there are a few more. And if you have them, send them to the chat. We got 2 answers. One student used sets, the other one used tuples. So we don't use tuples here at the moment because we don't have directions, so we have sets. So this makes a big difference from the notation. Later we will see tuples in the set, but right now it's undirected. So we got one suggestion to add 4, 5. Then we need 3 and 4. Then we need 2 and 3. And we need 4 and 6. And then we close this big set. So 1 and 5, 1 and 2, 5 and 2, 4 and 5, 3 and 4, 2 and 3, and 4 and 6. Are you all okay with this example so far? Maybe let me know. And as we defined in black up here, we said in general that V is a set of vertices. We saw then in blue this example, and for this example, we saw these example edges, Now we can think about how we can specify this mathematically and have a general description of the set of edges. What we can say is, remember, we looked at the Cartesian product, and this is something we will need now. We can have, say, our V, we can have V with itself, so a Cartesian product of V with itself. For these examples from before, this would be like 1, 1, 1, 2, and so forth. Because in V, we have 1 to 6. So we would have 1, 1, 1, 2, 1, 3, and so forth. But we will also have 2, 1, and so forth. We would have all the possible directions. This is what V with itself would give us. We can also write the Cartesian product of V with itself simply as V squared. V squared means Cartesian product of V with itself, and V are the vertices. So V squared will give us this set here of all the possible connections. And we have tuples in here, so this would be directed edges. But in our graph so far, we don't have directions, so we need to convert these directions into undirected edges. And what we also don't want for now, at least for now, we don't want a direction of a node with itself. That's something we will see later, and it will be possible to do this, that we allow such a link. And such a link in red is actually called a loop. So that would be a loop where a node is connected with itself. But at the moment, we don't want the loops. The loops will be forbidden for now. Or, well, I put them back, but the loops are not allowed for now. They will be allowed later. So 1, 1, this would be a loop where 1 is connected with itself. So we need to also kick out the loops. So we can think about now what E could look like from a very generic description. So we can say there's a set of connections. And we have X, Y, which come from V squared. So V squared we saw here. And from V squared, we have tuples, where we have a first element and a second element. But we want to kick out the loops, so we have to say that X must be different to Y, because we don't want the loops. So we want to get all the tuples from V squared except the loops. And because tuples would mean directed connections, directed edges, but these edges here are undirected, so we need to convert these directed ones into undirected ones. And undirected ones would be a set. So what we are doing here is we are converting this tuple into a set where we just say xy directed becomes xy where there is no direction, and we kick out the loops. And then the set of our edges is a subset of this big set here that I put here. Because this big set in yellow would be all the undirected edges possible except the loops. But typically for a graph, we don't interconnect all the vertices, but only some of them. That's why our E, so E came from up here, where I said E is the set of edges. So we can say E is a subset of all the possible edges in a graph. So this E is a set of edges. And so far, this graph is purely undirected, and we don't permit loops because of this one. I know this is highly generic, but now you see what we need our Cartesian product for. How do you feel about this definition? If you feel you understood it, thumbs up. If you feel you didn't understand it or you need some extra guidance, thumbs down, because all the graph definitions that are following will be purely based on this. So this is what we are using, and we will simplify it, and we'll have more specific graphs, but looks okay. So what we had so far are undirected graphs. I'm just writing the word here, undirected graphs, because these connections here, they connected two vertices, but there was no direction. The term graph should, from now on, always refer to this kind of mathematical data structure. Graphs can mean obviously something else. So a graph could also be some plot like this, where we have like a scatter plot or some function in it. That's a graph too, but that would be a graph, say, in statistics or in calculus, not here in this course. So when we talk about graphs, we always refer to this mathematical structure, not like visualizations or plots. Very importantly, that this would mean something totally different in statistics or calculus. Now we have our undirected graphs, and we got a question here. So one student asks, I'm just reading out the question. So apart from this particular example, would it be correct to say that the set of edges between given vertices is a subset of the Cartesian product of the set of vertices to itself? Yeah, more or less. So the Cartesian product gives us all these directed connections, and we would just make them undirected, and we kick out the loops. And the set of edges is a subset of the set here in yellow. And in yellow, these are all the possible undirected edges without loops. So you almost defined it perfectly, but you left out the loops, and the loops are important too. As we can define our graphs as this tuple of vertices. And there's a question. One student asks why above is why there is no yx. Maybe for the student who wrote this, you want to tell me more what your question is, because I don't understand the question. Or feel free to turn on your camera, your mic. You can also ask in German, since the question came in German.
Ja, so meine Frage wäre nur gewesen, weil Sie das E definiert haben, dass nur das Paar XY dasteht,
Ja.
hab ich nur gefragt, warum das Paar Y und X nicht mit drin ist.
Yeah. Okay. Danke. So I'll answer this in English. So this was about XY, and the question is why is there not YX in? So we have the tuple XY, and there's a tuple YX as well, obviously, coming from V squared. But since we convert the tuple to a set, we get rid of the order. So we would have two sets that are the same, XY and YX. But for sets, the order doesn't matter. And all of these sets are in a big set, so duplicate elements would disappear. So if we have a subset XY and a subset YX, they are the same, and they would disappear. Hope this helped. Maybe you can just signal, or whether you need to know, or should I explain in German again, since the question came in German?
Ja, vom Lehmann gepasst. Und wäre es in runden Klammern, dann müsste man die Reihenfolge beachten. Stimmt's?
Genau.
Okay.
So runde Klammern, Reihenfolge. So parenthesis means order matters, and later we will see graphs where the order matters, but here it's all undirected at the moment. And so we saw one way we can define graphs is a set is this tuple here, vertices and edges, but there's also a graphical way or more graphical way how we can define this. There are so-called adjacency matrices. So an adjacency matrix. What is that? I will show you a simple example. So we have a simple graph. 1, 2, 3, 4. Well, this. So we have 4 vertices and 3 edges. You could write them out as before, or we use a matrix. And the adjacency matrix would look like this. So we have this matrix, and we can put in some comments for the first, well, just place them here. First, second, third, and fourth column, as well as the rows. And what we put in here is a 1 if 2 vertices are connected, or a 0 if they are not connected. So 1 and 2 are connected. So I'll highlight this here. 1 and 2 are connected. So 1 is connected with 2, and 2 is connected with 1. So we put ones in here. 1 is not connected with itself, so there is no loop. That means we put in a 0 because there's no loop, and there are no loops at all, so the diagonal will be 0. And now I want you to think about what this whole matrix may look like. And you would just type maybe the whole matrix, these 4 by 4 values, so 16 values, and submit them here in the chat. And we'll compare your solutions and see whether you got this concept. So we put a 1 if they are connected, we put a 0 if they are not connected. So, we got a lot of good answers so far. So 1 is not connected with any other edge, with any other vertices. So we put just the zeros in here. And then this is a symmetric matrix. So the matrix is symmetric for undirected graphs. If the graphs are directed, it's not symmetric. So symmetric means symmetric along this diagonal. But that only applies here to the undirected ones. And then 2 is connected to 3 and 4. And so we also put the ones in here. And then we just need to fill in the remaining zeros because 3 is not connected to 4 and 4 is not connected to 3. So this would be our adjacency matrix for this graph. Do you feel okay with the adjacency matrix as a different representation? You should, well, I see only positive support. That's good. You should obviously test this at home, maybe write out the vertices and edges for this graph, as well as maybe come up with a adjacency matrix for this graph here, just for further practice. And now we will step by step, we will the question is about the symmetric part. So this is an undirected graph. So this matrix here is symmetric. That means you can reflect along the diagonal, the first diagonal, and then this would be symmetric. So we have this 0 here, the 0 here, there's 1 there, and 1 there. So you could reflect along this first diagonal, and that would mean the matrix is symmetric. But this only applies to undirected graphs, not to directed graphs. Hope this answered the question that you sent in the chat. And now we will step by step introduce new types of graphs. Now I want an undirected graph, which we had so far already done, but we want it to permit loops. So chi is again the vertices and edges, and chi is a tuple. V is as before, so V as before, V will not change. And E is again a subset of this big set as before, where we have X and Y are these sets where XY comes from V squared, but then we are done. Well, didn't look too great. So this is just the same definition as before, which we had done up here, but we had added that we don't permit loops, and now we permit loops. So we just get rid of this and, of this condition, and we say, well, we get x, y, these tuples from V squared. We convert these tuples into sets because it's undirected, but we permit loops. So the condition just gets kicked out. And E is a subset of this big set of all the possible edges. Do you feel okay with this? Just from the example before, we could change it obviously, and we could say, well, we are adding a loop to 2, so we would just put this 1 in here, and this 1 in here would refer to this loop. So that would be just a change to the adjacency matrix if we wish. And now we're almost done with the graph definitions because we have looked into undirected graphs, and now we can look into a directed graph. So a directed graph, it's again just simpler than before. We're just actually building something simpler and simpler. The graph is a tuple of vertices and edges, V as before, and E is now a subset, again, of a big set. And we have our tuples x, y from V squared. And for now, we don't permit loops. So we say again, x must be different to y. And so we take our tuples x, y, and we just keep the x, y tuples for which x and y are different. So this is a directed graph that does not allow loops, but we have directions. And we can look at an example as well, what this could look like. So we have an example, say we have 1, 2, 3, and 4. But now we have directions, so I'm adding directions 1 to 2. We have 2 to 4, and we have 3 to 4, but we also have 2 to 3. So 1 to 2, 2 to 3, 3 to 2, and 2 to 4. This would be a directed graph. Can you write me down what the set of edges would look like for this graph? Because V is obvious, but E, so I want you to tell me what E would be for this example here. I'll start with the first one because we have 1 to 2, and now it's very importantly, it's tuples because they are directions from 1 to 2. And you can go ahead with the remaining ones and send them here in the chat. So we got 2 to 3, 3 to 2, and 2 to 4. Well, that looks good. We can also think about an adjacency matrix. The adjacency matrix, again, 1, 2, 3, 4. 1, 2, 3, 4. And ideally, because this matrix will not be symmetric anymore, we would define that the rows are from and the columns are to. Otherwise, we may just have the transpose. So 1 is connected to 2. So I would put in the 1 goes to 2. The 2 goes to 3 and 4. And I want you to tell me where else I need to put a 1 in this matrix. In which field? From 3 to 2. That's correct. Well, just place it here properly. And all the other entries are 0 because these are the 4 edges we got in there. And 4 is not pointing to any other vertex. And as we have done this, we can still slightly amend it, and we can say, I want a directed graph permitting loops. What do I need to do if in this definition I want to permit loops? What do I need to change? You can turn on your mic or share it with us through the chat. What do I need to amend in this definition to have suddenly directed graphs that permit loops? Anyone still there? And well, that's correct. We have to get rid of this one here, of this end, because this kicked out the loops and we now want to permit loops. And what we see is that E is a subset of this here now, but we have xy coming from xy out of v squared. So it turns out when we permit loops, we can just simplify this and we can say E is a subset of v squared because we have xy coming from xy, but we have killed this constraint that did not allow loops. So we can just say now, when we have a directed graphs that permit loops, that E is a subset of v squared. Are you okay with this up to here? And now we only have, and I only see positive responses, and we will have the last graph. The last type of a graph that we will look at now is we want a directed, weighted graph permitting loops. So what's new is we before had directed graphs that permit loops, but now we want them weighted. And for weighting, I need one more component in my graph definition. So as before, a graph has a set of vertices, edges, and something new, a distance function. So V as before, it's just a set of vertices. E is a subset of V squared. And D is the new part. It's a distance function. And the distance function maps from an edge to a real number. So this is a distance function. What could this look like? I have an example for you that we can study now. So we have a graph where 1 is connected with 2. The weight is, well, I'll add the weights in color. So I just add the connections first. And the connection from 1 to 2 has weight 3, weight 2 from 2 to 1, weight 4 from 2 to 3, from 3 to 4, 1, and from 4 to 3, it's 2. So we need some sort of distance function. And how can we define the distance function? We'll see some examples in a moment, but I think it becomes easier if we first try to write this down as an adjacency matrix. So the adjacency matrix is again 1, 2, 3, 4, and I write here from 2 so there is no loop. Well, we actually permit loops, so we're going to add a loop. In fact, say we add a loop here, which is well, let's say not say 9. There's a loop from 1 to 1 with 9. So we would put that here as the first element. We would put the 9 because there's a loop from 1 to 1. There is a weight from 1 to 2, which is 3. So it's this one here. And then 1 is not connected to anything else. Do you have a suggestion what the next row could look like of this adjacency matrix? It's not just ones and zeros because this time we put real values in here, which are the weights. So 2 is connected to 1 with weight 2. There's no loop. 2 to 3 is 4, and there's no connection from 2 to 4, so that's 0. Then 3 is connected to 4. We would put a 1 here, and the 2 here, where 4 is connected to 3. So this would be the adjacency matrix for this directed weighted graph permitting loops. The only question is, how can we write out such a distance function? So the distance function maps, you turned on your camera, so you will be filmed and you're appearing. So probably smarter to turn it off. Good. And the distance function maps an edge to a real value. And what we could do is, as one example, if we try to define the distance function, we could say d of e, because it maps an edge to a real value. We could say this is a piecewise defined function that returns 9 if e is the loop, so from 1 to 1. From 1 to 2, we have this 3 from here. From 2 to 1, we have a 2, and so forth. So this 2 is here. So this is how we could define, for example, this distance function as a piecewise defined function which returns these real values based on the edge that we have as the input. It's one possible way to define this. And we have the adjacency matrix. Are you all okay up to here? I saw a question in the chat that I'll refer to in a moment. So all I developed on the iPad for you is here the graph definition, a graph example, undirected graphs, then the adjacency matrix. We have undirected graphs, permitting loops, directed graphs, directed ones, permitting loops, weighted graphs that are directed and permit loops. I didn't just want to show this from the slides, but rather develop this with you step by step. And we had this example here, and there's a question why I put the number 9 here as a loop. I just felt like adding a loop. So the 9 I put there as a loop was just the weight, could be -5, could be 1 million. So it's just a random value that I picked here. I hope this answers the question why I picked the 9, and then the 9 came in here. So just a random value that I picked. You can also pick negative values, not just positive ones or any other kind of real value standard for your use case. Then, what are graphs actually useful for? Graphs are a foundation data structure. In a lot of data structures, are in fact some variation of a graph, or a graph with certain constraints, like a list, trees. These are all graphs, but we can't arbitrarily connect the vertices. Rather, there are certain rules we need to follow. So we'll see graphs all the time. And there are a lot of craft algorithms. For example, routing. So you have a shortest path or lowest cost algorithm. That's something we'll investigate today for the remainder of the lecture. So how to get the quickest from one city to a different city. There are other problems. For example, you have multiple cities and you want to start in one origin city and visit every city ideally exactly once, and then return to the origin city. And what's the shortest possible route that visits each city and then returns to the origin? That's the traveling salesman or a traveling salesperson problem. Crafts can also be used for example dependencies. Say you want to import a package, but that package depends on other packages that you need to import first or load first. We could describe this also as a graph where a directed edge from one node to another one is sort of a dependency, and then we would do dependency resolution and figure out which packages we need and that we don't import the same package multiple times. Something like this could be done with topological sorting that will sort us these dependencies. That's also a well-known graph algorithm. And there are so many graph algorithms, you could have an entire module just about graph algorithms if you wish. Uh, you can apply graphs also to computer graphics. For example, if you have a polygon, so a polygon is a structure, and you want to know if a certain point in geometry lies within the polygon or not. That's the point in polygon problem, something used in computer graphics where you want to know if a specific point is in some polygon or not. For example, if you shoot at some in a shooting game at some target, you want to know whether you hit it or not. That could be done with the point in polygon problem. And there are obviously a lot of real world use cases. For example, a neural network is a graph. I want to train it. I can have knowledge graphs and want to make some inference in knowledge graphs. A blockchain is eventually a graph. So these distributed ledgers are graphs, and I want to manage some data in a distributed ledger. I could also find a clique in a social network. So a clique would mean that in a clique, all the vertices are connected with each other. So in a social network, that would mean they all know each other. It's a clique, a group of friends. You could find something like this in a social network. So there are lots of applications of graphs in computer science. If you know any other applications, just share them with us here in a chat or turn on your mic. But you're dealing with graphs essentially all the time. And we'll now look into two graph algorithms. They are highly generic and they are probably not that easy to grasp the first time, but all of this will become clear step by step as you practice and do your revision. Concretely, we want the so-called shortest path algorithm. And shortest path would mean, and for this, I will also switch back to my iPad. Just the iPad is unfortunately a bit slow, so it'll take a few seconds until I'm able to screen share there again. So should be coming momentarily now. And imagine I have the following problem for the shortest path. I I have a start, which is here, so start, and it's, for example, a city. And I have a goal city, and in between, I have other cities, and they are interconnected in some way. and I want to get from the start to the goal in a certain number of steps. For now, we assume the distances between these cities are the same. So this would be my start, and this is the goal. And then, obviously, when I just look at that, I would need three so-called hops. Sorry, more, four. One, two, three, four. That would be the shortest path because the other path would be one more hop. So these are so-called hops, just changing from one city to another city. Later, we will see the lowest cost algorithm where these distances also have a certain weight. So they're not all just the same distance, but there's a weight. And we will see then the lowest cost algorithm. And all of this is quite related to the Dijkstra algorithm, but we will not just look at that in terms of routing, because oftentimes these shortest path and lowest cost or Dijkstra algorithm, they are always interpreted from the sense of routing, that I go from somewhere to somewhere. But it turns out that we can generalize these algorithms, and we don't just do routing, we do search in a state space. So we have a start state and we want to get to a goal state. You could see the start state as the start city, getting to a goal city, but it could be some other state. It could be some problem where I need to take certain actions, maybe turning an object, filling an object, moving an object, and I want to get from one start state to a goal state, and I want to reduce the number of actions I need to do to get there. And there may be different actions, not just moving from one city to another, but there could be other actions, maybe taking a helicopter. And when it comes to moving objects, could be turning an object, could be lifting an object, could be filling or emptying something. And what I want is to get from a start state to a goal state. And that's why we don't discuss the classic Dijkstra algorithm. Rather, we discuss this shortest path algorithm, where we want to reduce the number of actions we are taking. And later, we will see, probably next week, the lowest cost algorithm, where we want to reduce the total cost, where these connections, where these vertices have a cost. And we want to not optimize for the number of actions, but reduce the number of the total cost. But that's something we'll possibly see only next week. Today, we start with optimizing for the number of actions. And not just from routing, but in general in a state search problem. And we will see some applications of that. Now, there is this shortest path algorithm. And we have a start state. We want to get to a goal state. And we want to reduce, and we assume that each action has uniform cost. So all the actions have the same cost, but we just want to optimize for the number of actions. And this is a so-called uninformed search algorithm. Uninformed means that these actions have no cost. So all the actions just count the same. And we want to implement a function now that we call shortest path, and shortest path will have three parameters. So I pass a start state, the start state from which I want to go, and I pass references to two functions. One function that generates successors, meaning I am in a state, which possible next states could I get? And the last function will determine if the next state I'm going on or going in, if that's actually the goal. And if so, I want to stop. And I not just want to find one path, but actually the shortest one. We will start implementing this, and then we look at examples, and then all of this will probably become quite clear. But it's a very abstract algorithm, so you need to spend enough time on your revision. And before we implement this algorithm, we need a little bit more Python. So we had the intro to Python today, And many of you had done Python before, and we will now use function references. Who of you has ever used a function reference or moved or maybe passed a pointer to a function? If you have ever done this, maybe let us know with a thumbs up. If you have never done this, a thumbs down. So there are some people who know the concept of a function, and that's cool because I'll explain now what this does. Imagine I have a function f1, and f1 just prints hello 1. And we have a function that we call f2 that we prints hello 2. It's just a simple made up example, but to show you the idea. Now I want a new function that I call execute, and execute will run one of these functions, f1 or f2. And I pass a reference to a function, and then, for example, execute prints starting, and it will print finishing. And in between, it will execute the function to which I have passed a reference. So when I call execute, I pass the reference to a function. The function does something, then does something at the end. And in between, it calls the function to which I have passed the reference. So I can call execute, and as the reference to a function, I just pass f1. So I'm not calling f1, but I'm passing a reference to f1, which is then stored in the parameter f, and then execute is executed. So it's starting, finishing, and executing f1. And so I could pass f2, for example. And some of you raised their hand that they had done something like this before. You can't do this that easy in other languages. In C++, you could have a pointer to a function, for example. In Java, that's probably more tricky. But here in script languages like Python, this works super easy. It may lead to lots of trouble in big projects because you don't know who is passing what and what gets executed. But here for this toy problem, this looks fine. Do you feel all okay now with function references and calling function references? Maybe just let me know if that looks okay. Good, because we will need this concept, because we will now implement the shortest path algorithm, and I'll explain it step by step. And later we will look at examples. So shortest path is a function where I have a start state, whatever the state will look like. Later we will see what it actually is. The exact structure doesn't matter of the start state. And then we have two function references. One function that we can call, and it will generate successors of our start state. So next states where I could go, maybe from one city to another city, where I move some object, whatever, depending on my problem. And I can also check if a state is actually the goal. And is goal and successors, they are implemented somehow. We don't care about this for now because we built a highly generic search algorithm where we just have a start state. We don't care what the start state looks like. We just know that successors and isGoal can work with the state format for that specific use case. And how they look exactly, that doesn't matter for now. And we'll see plenty of examples, and then this will become more obvious. So, and we are lazy. So maybe the first thing we want to check is if the start state is our goal state. That could be probably the simplest thing to look for. The state we are currently starting with, are we done? We could return just true, but we don't want to return true because we actually in this algorithm want to return a path. because we want to know what is the shortest path to get from the start to the goal. And so we should return the actual path so it can be executed later. So we could return just start, but start is a single state. And actually, mostly I'm expecting a path. And the path could be just a list. We've seen lists today in the intro to Python. So we would just return a list with a single element in that is the start element, and we would be done. Then, if this is the case, we are just done. We may not be done yet, so we need to continue. And what we need is a helper variable, and that's a so-called frontier. A frontier is a term from search algorithms, and the frontier contains potential states that I still need to visit. Concretely, and I have the definition written in the slides, and I'll show you this later. It contains all non-visited successors of previously visited states. But so far, we have not visited any states yet. So what we do initially is, because start is not our goal, so we somehow need to look now into the successors of start. But start has not been explored at the moment because it's only explored once we look into its successors. So the frontier is a list. That's why we have these outer brackets. But in the frontier, we not have single elements, but actually in the frontier, we will store the whole paths. And the initial path we're just starting with is just a single element. But later, we always expect to have paths in the frontier. So the simplest thing we can do is we put start also in a list, which is just this very short path. And later there will be longer and there will be multiple paths in it. But we are now in the process of exploring our frontier, and we will soon take out the start state. And what is important at this moment is we have another helper variable that we call explored. And in explored, we will always put in what we have explored. And we're just starting to explore the start state. So we can just say we have a list of explored states and that's start. But later we need to check if other entries are also, so later we will explore new states and we need to check whether that state has been explored already. Because we want to avoid moving back and forth, always re-exploring states that we have already looked in. Because once we have finished with a state and we ever come back to it, we have already explored its successors. So we should exclude states that we have already looked at, and we could do some lookup in a list, but the lookup in a list that is unsorted is inefficient. So Python is very helpful because it offers also a set data structure. We've seen sets before around the Cartesian product. So in a set, the order doesn't matter. Duplicate elements are not allowed. And the good thing is in Python, we can do very efficient lookups on a set. So we put in the start state as a list, and we convert this list into a set. And later, we keep adding to this explored just the kind of states we have already explored, or once we have started to explore them, we put them in explored, so we will not re-explore them unnecessarily. Are you all okay up to here? These are the helpers we need, and now we will actually start exploring. It could happen I don't find a solution. Maybe there is no way to get from a start state to the goal state. That could happen, in fact. And if that happens, we have to return later an empty, um, like a fail. And a fail would be oops, sorry about that. So at the very end of the algorithm, we would return a fail, but we're not returning a false, but we are returning an empty list, which means there is no path to get from the start to the goal. And now we got a little bit of work in between because as long as there is still something in the frontier, we can continue. And Python is like pseudocode that I can execute. And this loop here says it's a while loop, and it keeps running as long as there's still something in the frontier. And currently we have this list, this path in the frontier. So currently it will keep running. Then we have a couple of things to do. Um, it could happen there are multiple elements in the frontier because later we keep adding paths to the frontier. And when we add to a list, we always add to the right. So to the right, there will always be more elements. But which one do we pick now and explore in the frontier? We pick the leftmost one because this one has the lowest number of hops, so the lowest number of actions. Because when we add more, there may be more with more actions, but I want the shortest path, so I have to take the leftmost one. And one student here said something in C, well, long time ago in the chat, but I guess since this came 12 minutes ago, it somehow only popped up now. If there's still a question from before, let us know. And so I need to pick the leftmost element. So what I could do is I could say I want a path and I take the frontier at element 0. Because that would be the leftmost element. But I not only want to take it, I want to actually take it and delete it from frontier because I'm going to explore it next and I want to have it out of frontier. So the Python list offers that I say pop at index 0. Popping means remove and return the element at that index. So I'm getting this path. So for frontier, initially, there's only one path in here. I pop it, that means I delete it and return it to path. So it's removed from frontier. When I have more elements, it's simply the leftmost element. Then, now I need my state, and initially, so path will just refer to this list. So what I could say is I just take the element 0 out of here because in this list, there's only one element, which is 0. But later, there will be multiple elements. So these paths, as we build them later, they will be composed of a state, then an action, then a state, action, state. So we're going to add a lot of action and state pairs to these lists, which are our paths. And it could happen that this grows quite a lot, but I only care about the current state. So once I have walked a path, I only care about the newest state. So it's not 0, but it's -1. -1 means in such a path, I take the rightmost element, which is the current state. I know this is all highly generic, but there will be some coursework and some exercise to better understand this. So don't worry. What I need to do next now is I have that state, which is the current state of my current path, and I need to see which are its successors, which are the possible next states I could take from that state, and which actions. For this, I need the successors function, And the successors function later will be implemented in a way that I pass a state, which is my current state, and it will return me possible actions and possible states. We have introduced today these so-called dictionaries. And for the dictionaries, what I can do is I can add these key value pairs. We did this in the morning in the Python intro. And when I call on, so successors will be eventually a dictionary where I have a key value relationship, where a key will be the next state and the value will be the corresponding action. So successors will return me a dictionary for my current state where the keys are states and the values are the actions. And if I call on a dictionary in Python, the .items method, it will return me a list of tuples of states and actions. We will later run all of this code, so just bear with me that it works this way. So I need to iterate over this list, or it's actually not a list, it's an iterator that will return me state action pairs. So for my state action pairs in successors on S, where I return all the items. So I have a loop, so I need to put the colon here. And just to make this more understandable, I call it state and action. Then I've told you before, when I look into successors of states, we may run into states that we have seen before, and they have been explored already. We don't want to look into them again, so we will say if state is not in explored, only then we will continue. Because if we have seen this successor state already from somewhere else in the graph, as we progress, we've already looked into it, we don't want to see it again. And because this successor state will be explored now, we say, well, explored at state. This new state we are looking at, it will be added to this set, and we won't be using it in the future again. We won't be investigating in the future again, but now we're going through these successors, and we don't want to see that specific successor again. Now, we're almost done. The algorithm is just maybe 5 more lines of code. Because this new state could be our goal. We could say, well, what if this new state that we got as a successor, and later you will see for concrete examples what a successor and isGoal function could look like, but how they are implemented, it doesn't matter here in this generic search algorithm. So it could happen that our next state is actually the goal. And if so, I need to return something. So what I could return is my path, which I had here, plus something on top. As we can concatenate strings in Python, we can also concatenate lists. So path is a list, and I can concatenate it with another list, and then this will finally create a new list that is being returned. And we concatenate our path with an action state sequence because we said our path starts with a state and we have an action to get to a specific state. So we return this, and that would be the solution if this new state is the solution. However, it could happen that our next state is not the solution yet, or the goal. That means I have a new path that I need to add to my frontier. because the frontier is always the stuff I still need to explore. And here would be a quick change of the code. So what I called here path concatenated with a new action in a state, this will be a helper variable that I call path2 because path2 is the new path. So we just call it here path2. It's just what we did before. The path concatenated with an action and a state becomes a longer list. And if this is not the goal, then I need to append something to the frontier. And in Python, I can append to a list. Appending means adding an element to a list. And because frontier is a list, I'm just going to append, so at the very right end, another path. In a few weeks, you will also learn how to build your own lists and how to append, how to pop. But here we just use the standard Python list. So this is our shortest path algorithm. We start with a frontier, which is just our start state. We remove the start state from the frontier. We look into its successors. However, the successors are defined in the goal. And then we see if the successor is the goal. If not, we continue. And because we always append to the right, so to the rightmost end of the frontier, and we pop from the left, this guarantees us to actually get the shortest path. Shortest path in terms of the number of actions. The actions have no weight at that point. Do you feel okay with this up to here? I know it's highly generic, and we will now actually use an example to make this more understandable. For this, I will switch back to the slides. What I said is we have the start, successors is goal. I've already talked about this. Here it's again in the slides. And in some of my slides, you will actually see a lot of text. I don't read out this text, but this text is for you, for your revision, or if you forgot something, there's a lot of text in here in some of the slides. It's mainly for you for revision, so you don't need to look up into a book at that moment, but rather you can just look into the slides. And I've said before that the frontier contains all non-visited successors of previously visited states. And it's sorted by the path length in ascending order. That means to the left, we have the one with the shortest length, and to the right, we have paths that are longer. And we always pick the left, always append to the right. And this algorithm is guaranteed to return the shortest path if there is one. If there is no path, it will return a fail. And this is what we just coded. All we did, we just flipped these two lines in the explanation, but that doesn't make a difference. And all the other stuff works as it's put here. The only thing is here in the slides, I return fail and I define fail outside the function. In the coding example, I just put the empty list here, but that doesn't make a difference. If you want to code this on your own, I have a very important advice. Don't copy paste from the slides. This will probably lead to chaos, also with the indenting. But in the Nextcloud, we have this resources.zip file, which would allow you to download a lot of scripts that we need in this class during the term. And you would also find a file for the shortest path that you can use. But for good practice, you should probably implement this again on your own line by line. And now we will look at an example. The example is not a routing problem because oftentimes these algorithms are just used for routing. But this time we will do the so-called pouring problem. And it's a state search problem. And I will present you this quickly on the iPad. So we will have the pouring problem. And the pouring problem works the following. We have two classes, and these classes have different capacities. So we have class 1 and class 2. Class 1 has a capacity of 418, I don't know which units, say milliliters, and class 2 has a capacity of 986. And initially, so for the start, both classes have zero capacity, zero filling. So the capacity is 418, 986, but the classes are empty. And we have a few valid actions of what we can do. We can totally empty a class. We can totally fill a class. So we could totally fill the left class, or we could, in a different action, totally fill the right class. We could totally empty a class, or we can pour from one class into the other. But clotting is not legal. So you're not allowed, say, if to keep pouring if one class is full. You wouldn't be allowed to do that, to just keep pouring and pouring that it swaps over. You're not allowed to do that. So you can fully fill a class, you can fully empty a class, or move the content from one class into the other class entirely. And what we want is we want to know how many of these legal actions we can take. So fully fill, fully empty, fully pour from one into another. And our goal is that the left class will have capacities, will have filling 6, and the right class will have filling 0. This is our problem. So it's a state search problem because we start with states 0, 0, and we want to get to 6, 0, while we have the following legal actions: fully fill a class, fully empty, fully pour over, not just partially pour over. What do you think, how many actions it would take to get from 0, 0 to 6, 0? You can make some guesses here in the chat. I just want to collect some guesses. What you think, how many actions we would need as the shortest path, so the minimum number of actions to get from 0, 0 to 6, 0. Please send some guesses what you think it could be here in the chat, and later we'll see the solution. So one person guesses 22. Please send some more guesses because we'll compare. So we have guesses 17 up to 32. Maybe there are some more extreme guesses, like one person guesses it takes 6 actions, 1, 8. Maybe anyone guesses it could take far more actions. One person says more than 100. So your guesses are, well, 0, not 0, because 0 would mean we're done. And 0, 0 is not the solution. So 6, 0 is the goal. And so we have guesses from 6 to more than 100. So there's a big range. So someone guesses 508. Also, fine. We will implement this now. And for that, if you try to solve such a problem, it's typically a lot of strange code that you need to write. So we are going to use the shortest path search. Imagine you did not have the shortest path search we have just implemented. If you didn't have that, it could be quite tricky to solve this problem. You may need to write a very strange algorithm that typically would not work in the beginning. You need to do lots of debugging, and you cannot really reuse it for other problems because you just mix up the actual shortest path search with the actual problem, which is here the pouring problem. And we have separated the shortest path search from the problem because we have the shortest path search, which you have seen, it doesn't care at all about what the states look like. And there's a question here. One student says he doesn't quite understand the legal actions. Is he allowed to fill the right class and pour it into the left one and have something left in the right one? No. So you're not allowed to fully fill the right class and just pour a few milliliters into the left one. You can only fully pour from one class to the other. But you're not allowed to pour over. Say, if the left class is almost full, you're not allowed to pour over from the right. And you're not just allowed to pour over 6 milliliters. Your valid actions are only fully fill the class, um, fully empty the class, or pour as much as possible into the other class and keep some in the right class. So if the left class if has some filling, you move from the right one, you can fill it, but there is something left in the right one, and you cannot just pour it out then or artificially reduce it to 6. But this will become more clear when we start implementing it. And you will see that this becomes quite interesting, and you have a lot of guesses. Some people think it takes 6 actions, some think it takes 100 actions, and someone thinks it could take 508 actions. And we will see this now. And when you try to implement this without the shortest path search, your algorithm probably will not work. And even if it works, you cannot reuse it for a related problem because you mix up search with the problem. And what we are doing is we have now the graph search, shortest path search, and we can use it for lots of different state search problems, like the pouring problem and lots of other ones. And we only need to define our state format, as well as what we also need to define is the successors function and the goal function. And for that, I have this slide here that I just talked about. So this is the pouring problem. And it turns out the pouring problem is part of the coursework. So we're doing the coursework together now. Problem 7.1 is the pouring problem. And there's a lot of code in here that I will now show you how to implement, and we will discuss what it actually means. And for this, I will switch to my terminal, and I'll show you what the essence of the coursework problem 7.1 is about. So I have a start state. Start state is 0, 0. In the left class is 0, and in the right class is 0. Then I need an isGoal function, and we can have isGoal where I pass a state. So a state is always a tuple. So like we have lists in Python, we can also have tuples in Python. Tuples are like lists, but you cannot change them. So they're immutable. So a Python tuple is like a Python list, but you can't change it. So it's immutable, what we say. So we would check in the isGoal, we would pass some state, and we would return if state is equal to 6, 0, so that the tuple is 6, 0. And if that's the case, we return true. If it's not the case, we return false. So you see, we have already implemented two components for shortest path search: start and isGoal. And later, we want to call shortest path on this. Path start isGoal. The only question is now the successors. This is somewhat more tricky. And we will start with this. So we have a successors function, and I first simplify this a bit compared to the coursework. So we have a successors function for which I pass a state. And that's exactly what we need here, because you see, in our implementation, we said there is a successors function. This doesn't look nice, sorry. We have the successors function for a state, and it will return from a dictionary the state action pairs. And the isGoal function is also called in here for a state. So we have already implemented isGoal for a state. Now it comes to the successors function. And we have our state, which is a tuple, and it turns out we can break a state into, if the state is a tuple of two elements, we can break this into X and Y. This works natively in Python. So if state is a tuple of two elements, the first entry will be in X, the other one in Y. If I pass some other object or whatever, then this will obviously lead to a runtime error. And now I need to return a dictionary. We've seen today in the intro to Python how I can build a dictionary, and we can do this fairly easily. What we need in here is we need these capacities as well in our successors. So we have the capacity of the left class is 418, and of the right class, it's 986. Are you all okay up to here at the moment? It looks a little bit different to the coursework sheet, but we will later evolve into what we have in the coursework sheet. So 418 and 986. And now we return a dictionary. Oops. Where we have our 6 actions. And we always have these key value pairs. So we have a successor state and an action. And an action could be fill the left class. Completely fill the left class. What do you think this tuple would look like? If you can also turn on your mic or send this in the chat. What do you think the tuple would look like if I take my state and I fully fill the left class and not touching the right class? So one person suggests 418y. That's correct. But we keep the capital X because we may want to change this at some point. So we want to generalize a bit. Then we have another action. We want to fill Y. What do I need to do to fill the right class? So we don't touch the left class, but we completely fill the right class. Then we have two other simple actions. We want to empty the left class. What do I need to do if I want to just completely dump what's in the left class and not pour it anywhere? Zero Y. And then you can guess what's the other one, empty y. I keep x and I empty the right class. Now, these were the simple ones. Now the pouring becomes a bit more difficult because I need to implement how to pour from left to right. And I need to I need to implement how to pour from right to left. And this is a bit more difficult because there are two cases. One case could be I can simply move or pour everything from left to right because there is enough space left in the right class. So if I'm able to do this, means the left class is empty and the right class would be just y plus x. Because I can just pour everything from left to right, it will fit in. And the good thing is, this is a new syntax probably to many of you, but this makes it so convenient in Python. I can say I only have this key if x and y are less than or equal to the capacity of the right class. So only if small y and x are less than the capacity of the right class, only then the tuple will look like this. Are you still with me? Does this make sense to you? I only get positive responses. And then we have the other case that is more tricky, that I can only partially pour from the left to the right class so that the right class is full. But I have something, so this means the right class is full, but in the left class, there is something left. So I have to subtract the difference of what still fits in the right class, because y is the current filling of the right class, and its capacity minus the filling is as much as how I can pour, and that's what I subtract from small x. So that's what I can pour over, and then the right class is full. And I want you now to think about what the next line could look like, maybe without looking into the course worksheet, but how I can pour from right to left. It's just the same structure and I need to amend it. So I'm curious to see if you got any suggestions of how I can pour from right to left. I'll wait 1 or 2 minutes and see if there are any suggestions here in the chat. So it's more or less the same as before. There is some condition, otherwise there is something. So one student suggests x plus y and the right class is empty if x plus y is less than or equal to x, yes. Or you can rethink the first two answers, can rethink. The third answer looks great because the left class will be full then, capital X, and in the right class, what we've got left is the difference of what we can pour. So this was suggested by the third answer, which is correct because the other answers, they didn't amend the last case fully because this time we move from right to left and then left could be full and something could be left in the right one. So we have now implemented the successors function for these 6 actions, and these actions are gone through in the shortest path, and dot items always returns um, eventually all the key value pairs. So the key is the state, which is this one here, and the value is the action, which is this one here. That's why we also discussed the hash tables or maps earlier today. Now we are ready. We can run it and see if it actually works. We can say we have the result. We call shortest path. Well, not like this. This is just what the auto completion suggests. So we call this on the start state. We pass a reference to the successors function, and we have the reference to the isGoal function. And there's a minor typo that I made before. I already felt that there was some typo in my initial algorithm because successors needs to be spelled with 2 C's. When I looked at it, it didn't look too great. Obviously, in the slides and in the resources files, there are no typos, so I missed a C. And let's see, but this is live coding. Let's see if it's running now. So something has happened. We have run length, and we have run it, and we can see what's inside actually. In res, a we have a relatively long path that has 1,237 elements. Now, what does that mean? We can try to look into res, what's inside. And what we get is something relatively cryptic because we see it starts with 0, 0, then it fills right. So this was the state, then an action, then the state, then the next action, then the next state. So it starts filling right, then moving from right to left, emptying left, moving again, and so forth. And eventually there are 1,237 items, meaning a state, an action. And now, how many actions do we have in here? Well, that was the thing we wondered about. So we need to take the length of res and divide it by 2. So, because we don't care about the states, we just care about the actions. And what we get is 618. So we needed 618 actions as the shortest path to get from 0, 0 to 6, 0. Are you surprised it took that many actions? If you are surprised, send some reaction. If you're not surprised, send something different. And this is the shortest path. By the way, here, division in Python. You are used to division from Java. If you do 3 divided by 2, you would get a 1 in Java because it would be integers. But in Python, this is a float division by default. So we need to say 3 as an integer division by 2, which is this one. Alternatively, you could do also 3 divided by 2, which is 1.5, but you convert it to an integer, then you get the 1. So the division works different than in Java. So, a lot of actions, and we will just slightly improve this now. I mean, not in terms of code, if in terms of the result, but the code. What I had here was the shortest path function, and I defined my isGoal function. There's a question, why is this an odd number? Because we start with a state, so we have one state, and then we always add 2 on top. Action, state, action, state. So the result will always be an odd number, which is the number of elements in this path. because we start with a state, we do an action, and then get into a state. But we have to divide by 2 with an integer division to get the number of actions, because there is one more state than we have. So there, the number of states is +1 compared to the number of actions. Hope this answered the question. There are lots of extra notes and hints I want to give for today. Because if you look into the course worksheet, which I'm sharing now, you will see more or less it's the same, but the code does a little bit. Oops. Is the screen share working at the moment, or did I miss it? Maybe just confirm.
Doesn't work.
Okay. Now should be working. When you look into the coursework, then what we do in here is we call the shortest path, but it looks a little bit different. And I just want to show you a little bit more Python so we can actually understand what's going on. Because we have the successors function looks somehow different. We also see the isGoal function does not exist, but it uses a so-called lambda statement. And all of this will probably it's a little bit of syntax, and I will show you this now in Python, but it doesn't add anything new from the theory perspective. So we did this one here. So we called the shortest path. And we had this isGoal function, which checked whatever. But the isGoal function is actually very, very simple, and actually too simple to define a new function. And that's why in some programming languages, there is a so-called lambda statement. And lambda, has anyone seen lambdas before in other programming languages? If so, maybe let us know. Lambdas are implicit functions. So rather than putting a reference to a function I have defined, I can just put a lambda here, and the reference to this lambda will be passed. And this lambda only has one parameter, and the parameter is state. And if state is equal to 6.0, then this lambda will return true, otherwise false. So it just works the same as before. We just don't need to define the isGoal function. And what we can also do is we have the successors function. The successors function can be improved. It can be made more generic. Imagine I have this 418 and 986, and I want to change it. I don't always want to touch the successors function and change it. Rather, what I wish to see is if this could somehow be passed as a parameter. So x and y could be passed as parameters. But if I change my successors like this, it doesn't work any longer in my algorithm, because the shortest path will call successors on a state, and it will not magically pass something here. So this doesn't work very well. What we can do is we can build a function within a function. And that's probably the last Python detail for today. Who of you has ever done a function within a function? In any programming language? One person. That's good. And what we can do now is we can use successors to customize x and y, and we would later pass successors up here with our reference or with our values for x and y, but internally in successors, we have this actual successors function on the state. So I could say within successors, there's the actual successors function. You can guess what I need to do now. I need to indent properly after moving this. And when from outside we call successors, we will not run this inner successors function, but actually we return a reference to it. So what we do here when we call shortest path, I can pass my parameters to successors now, which was 418 and 986. When successors gets executed, it will store these parameter values for x and y, and it will return SC, and SC is a function, so it's returning a function reference. And then this function reference is the actual successors function that is used within the shortest path search. So this looks quite complicated. In fact, it's not, because what I can do is very easily, I can customize 418, 986. What you would also see in the coursework is 00 rather than start state. And there's a question about the exam. I'll respond about the exam later. Exam doesn't, so at the end of today. And rather than passing a start state variable, I just have the start state here, which is the tuple 00. I have the successors customized, and this will return a reference to SC, which will be used internally in shortest path, and I have this lambda. And if I run it, what you see is I still get the same answer as before, but I can now customize this more interestingly. Imagine I want to customize this to 121, not 986. So what we get is a length 0. What would this mean if the length is 0? You can let me know either through the chat or audio, a fail. So it's not possible. There's no solution to get from 0 to 0 to 418 and 121. To get from 00 to 60 by having these capacities. No solution. So we don't just find here the shortest one, but we actually find out there's no solution. We can put 122 and then see, and it turns out for this we need 186. We could also change the goal, for example, like this, and figure out no solution. Put in a 2, also no solution. So you could try out some settings where you would see if you can actually find some settings that work, some settings that don't work, and whenever you get a solution, it's the shortest path. One last thing. Building this dictionary here was a lot of syntax. Did you feel this? Did you personally feel that this kind of syntax here is challenging? If you feel it's challenging, somehow let us know. If you think it wasn't challenging, let us know too. But I think if you're new to Python, this doesn't look really nice. There's a question here, how do you know the difference between start state and goal state, and there's no solution? So this is the start state, this is the goal state, these are the capacities, and if the if the result is an empty list, there is no path. So that's how you distinguish. And I totally understand if this here looks complex. And it's a lot of strange syntax. And now imagine you need to build an even more complex successors function. Maybe this is not too cool. What you could do is you could build this also step by step. You could say, for example, your result is an empty dictionary, and then you could build the dictionary step by step by adding the elements. So you would say, my result is an empty dictionary that I'm adding this key and this value. You would then do this here as well. So you could step by step compose your dictionary. Just need to fix the syntax step by step because probably not the only person who responded found this challenging. And then we could say we're building this. And now we could do something else. We could say if this is the case, then we add this to the dictionary. Otherwise, we do this one here. So with the same action. So we are converting this step by step. So we say if this condition holds true, we put this value in the dictionary, otherwise this value with the same action. And you would still need to do this last line and convert it, and you would return result here. So, well, I'll still do this for you, and then you see what this dictionary, would look like. We're almost done. If this, otherwise this, and then result of this. So you would just compose this dictionary step by step and then return it. So for the ones who found the previous big dictionary challenging, is this something you would maybe feel more comfortable with? So you could just build your dictionary like this. Maybe just let us know if you prefer this new one here. If this is something that maybe step by step you build a dictionary rather than having this big dictionary where you mix up the conditions with the values or the keys. So this would be also a way to build it. I hope there's no bug in it. Maybe there's a typo or something. I don't know, to be honest. But you would need to run it. Well, we can run it and see if it actually works. So the successors get updated. We wanted 6.0 and capacities was 986. So still works. So I've just made this maybe a bit more readable. You would still add some empty lines and maybe some comments. So you can also build your dictionary like this. And congratulations, you have just finished problem 7.1 of the coursework. What I would advise you still is to spend again time on the coursework, play a bit with the values, maybe run this through a debugger because we have now functions within functions calling other functions. So a debugger could be in fact quite helpful to see all of this. And we have a few minutes now left of the lecture. Um, so we've built the shortest path search, and you've seen an example. And obviously, we could use this for routing as well. You have a start city, a goal city, and some cities are interconnected. And if you're in one city, you have possible successor cities that are directly connected with our city. But as you see, we can use this for far more and not just moving between cities, but we actually have actions and different actions at a time. So it's a much more generic search algorithm than the standard Dijkstra algorithm. So the standard Dijkstra algorithm is a very famous algorithm that finds you the shortest path between nodes in a weighted graph. We have not used weighted graphs yet, as you've seen. We have only reduced the number of actions, but we have not given any weight to the actions. So Dijkstra's algorithm would work on a weighted graph. You could use this for a road network or for other stuff. This was proposed or derived by Edsger Dijkstra, a very famous computer scientist, I think in 1956, and published it 3 years later. And that algorithm works on a weighted graph, but it also finds not only the shortest path from a given source to the goal, but to every other node. So it gives us a solution to every node and not just to the goal, which is quite cool. Today, we have only done unweighted graphs where we reduce the number of actions, and we have called this algorithm shortest path. Next week, we will see the lowest cost algorithm. But I still want to emphasize why our approach here is so interesting. Because we have separated the actual search from the problem. Because things like the pouring problem and other problems, for example, there's a coursework problem 7.2, it's the so-called missionaries and cannibals. It's a different optimization problem in which the states look different. You would need to come up with a different state format, different goal function, different successors function. But for these missionaries and cannibals, you can just have a single successors function where you pass the state. You don't need in problem 7.2 these overly generalized successors with these parameters. So you would just have a single successors function that returns a dictionary, has a state as a parameter. You don't need a function within a function. And next week, we would see the lowest cost algorithm for which we actually have one more parameter in here, which is an action cost. So we can define costs for actions. But the beauty here is we have separated search from the problem, so we can easily reuse the shortest path search for other problems. All we need is a state format, successors function, and goal function. You may think all of this looks quite old. The Dijkstra algorithm is from the 1950s. It turns out this is still, people still do research on this work because the there was something in the news like last year or something in which the in which a Chinese research group claimed they came up with a new, better search algorithm for graphs. And it really looked like, they have broken a 40-year-old record and they have come up with a new algorithm that is generally better than existing graph search algorithms. This was popularized in the news last year, but there was also a lot of wrong information. They published an interesting algorithm that runs faster than existing graph search algorithms on a specific type of graph where certain constraints are satisfied, not in general. Very importantly, but for those types of graphs, that algorithm runs faster. That's true. And not just faster in terms of the running time, but a better complexity. Complexity is a concept we will see next week. But yet, this was extremely exaggerated in the media. And shortest path search is not just done by computers. I found two very interesting YouTube videos, how water finds the shortest path in a maze, or how electricity finds the shortest path in a maze. Um, you don't need these two here for these two videos for the remainder of the course, but if you're just curious, or it's the same video in fact, but the first part of the video covers water, the second one electricity. Feel free to watch the video in case you're curious how nature finds the shortest path through water or electricity. Next week, we will look into the lowest cost algorithm plus some other algorithms and then look into complexity. There was a question about the exam. If in the exam you need to be able to come up with some of these functions, like a successors function or something. It's something I have not, I think, covered a lot in past exams. And if you would need to come up with a simple successors function, this would be relatively simple and not some overly complicated one for a problem because we just don't have time for this in the exam. Yet, maybe for now, don't focus on the exam, focus on understanding the content. Make sure you understand everything. But probably in the exam, I would not quiz you to come up with some overly complicated successors function. And um, one student asked about a course that he or she has not seen priority queues and heaps in the slide. We don't really cover these two data structures. We unfortunately have limited time. I think at some point I will briefly mention heaps and priority queues, but they are not a focus of this course. We will see heap sort as an Outlook topic. We will see queues quite a lot, but we are unable to discuss priority queues and heaps in great detail. There's a question if you need to revise everything up to 7.2 until next week. No. Until next week, what you should make sure is you're okay with Python. So spend enough time on the Python primer. There are lots of exercises in the Goodrich book. We have the intro to Python file. If you're new to Python, focus on Python until next week. If you are already okay with Python, maybe look into problem 7.2. But I'm there in the lab next week, Friday morning from 8 to 1. So whatever questions you may have about the content, about Python or whatever, I'll be happy to help. One last thing about next week. Next week is the last Friday before the Easter holidays. So in 2 weeks, Easter is the beginning of the Easter holidays. So in 2 weeks, we will not have class at all on Friday, which is Friday. Let me just check which day in the calendar. Friday, the 3rd of April. But I want you to have enough time for revision and enough content for the Easter holidays. So next week, we will also do a double lecture. So next week, we have 3 lab sessions from 8 a.m. to 1 p.m. You can pick any lab session you want. And then we have a double lecture next week as well. But the double lecture will probably already start at 1:30 p.m. But I will still send you an update in the coming days in the iLearn course about next week. But please come to one of the lab sessions in the morning if you have issues with Python or you would like to understand the pouring problem in greater detail or whatever from the course, because I want you to succeed. So come to the lab and take advantage. Are there any other questions up to here? There's a question if LeetCode problems are a good source. Feel free to do LeetCode if you got some extra time, but maybe focus on the coursework here or the Goodrich book, because this is the kind of stuff I have picked because it aligns the best with our lecture here. But if you do extra work, obviously you're welcome to do. So, with there not being any further questions, I wish you a great weekend. spend enough time on revision. If there are any problems, let me know or come next week to the lab. And then we'll continue next week with another double lecture. And I know today was quite intense, but in 2 weeks you have the Easter break also for revision. So I want to make sure we have a head start this term. And then there's also enough time for you to work on the lab problems. If you feel super comfortable with everything, you can start already the mandatory problem because this content is explained entirely in the book. So there's enough workload for everyone, no matter on which level you're starting. And I'll stop the recording and see you next week. Have a good weekend. Bye bye.